Hello, welcome back to a video series on MAC 1140 Precalculus Algebra. My name's Sean Perry. These are the guided notes number 5 in the series on section 1.5, Polynomial and Rational Inequalities. Let's first recall how to solve a linear inequality. We could solve such an equation for x. If I minus my 4x over to this side, I would have minus 12x plus 9 plus 5. I'm actually going to do something a little odd here. I'm going to minus this 5 over, not because it's the most direct way to solve this inequality, but because we're going to be looking at polynomials soon. And polynomials we don't solve just by going through inverse operations. We have to use the factoring and the zero product property. And setting it equal to 0 will be something we'll do much more frequently than just going right for solving for x. So let me show off this method, and that lets me do something else. It lets me remind you that when we are dealing with inequalities, and I want to divide by a negative, like dividing by this negative 12 here, I must flip the direction of my inequality. Now, to graph a one-dimensional inequality, we really just need a number line. We would mark 1/3 on such a graph. If there were more tick marks, we would do that way. Here, I am going to now shade. So we leave this open to show we're not including it because this is strict inequality. And we shade all the regions above it because we are looking at a greater than, right? The symbol expands towards x, or, it is a hungry alligator and eats the bigger number. However you remember it, just remember that we are shading above the 1/3 when we have x is greater than 1/3, or correspondingly 1/3 less than x. Both mean the same thing. Moving on. This graph asks the question, where is the graph greater than 0? Notice that it says greater than or equal to 0 here. Well, quite simply, that's where the graph is above the x-axis, which we can see is in these two regions, or where it's hitting the x-axis because we have or equal to here. So that's these 3 points. Now, how do I demark these regions on the x-axis in interval notation? I would go from -infinity up to -3 and include it, because we have equals. This is inclusive inequality. We include it with a bracket. Then we union that together with the closed interval from 0 to 2, brackets all around, except for at this -infinity, which we never include. So we should let this be a lesson about a visual digestion of what these inequalities mean. When is it greater than 0? It's when it's in this top half plane here, when it is above the x-axis. Likewise, this graph is asking us, when is it above the axis or strictly without being equal to 0? Well, here we have such a region all above this point, meaning all these x values will have this be true of their f of x values. Now, this point is a 0, but we're not including 0. So that point wouldn't get counted into our answer set. All that would be counted is -infinity up to -2 and not including it because this is exclusive inequality. Now here we have a fully fledged algebraic version of the problem. No graphs. They just want us to answer, when is this thing positive? When is this parabola positive? And we could answer that by graphing, but it will be more illuminating for us to try to solve it. Now, if I solve this, so to speak, if this were an equality and I tried to solve it, I would factor and set it equal to 0. Now, factoring this quadratic equation, we'd put an x and an x, we put a minus and another minus to make a plus, and we say factors of 12 that have a same sign sum of 8. That's going to be 6 and 2. So here's the idea. If I were to graph a number line, what I should do is mark the roots of 2, +2, and +6 in order. And the idea is that the only place that this could go from either being positive to negative or negative to positive is going to be where the polynomial passes through a 0. That's the intermediate value theorem from the last section. And what this intermediate value theorem can be used to say here is that we could test points outside of these regions and see whether or not it's positive or negative in those regions. And all we need to do is pick one such point. So a convenient point that is less than 2 would be 0. And plugging in a 0, we would get, well, -6 times -2, but that's a positive number. So let's just mark positive here. And now we could pick a number. We could pick a number in this region, like, I don't know, 3. And plugging it in here, we'd get a negative. And plugging it in here, we'd get a positive. And so we know that this region here must be negative between these between 2 and 6. But there's another way to do it. We look at the multiplicity of the root 2. And the idea is that if it has an odd power here, then there will be a sign change in going from one side to the other. And because of that, we could say, hey, look, this thing was positive. It must be going to negative because this has odd multiplicity. And likewise, at the 6, this also has a odd multiplicity, a 1 power here where I don't see anything. And so going from here to here, I must change sign again. That will happen, right? And we could also see that plugging in numbers greater than 6 would give me a positive in both places, and so a positive overall. And so we can use this to answer our question, when is the original function greater than 0? Well, it's going to be greater than 0 from minus infinity up to 2 and from 6 up to infinity. We don't include the 2 or the 6 because this is strict inequality. Here's a lovely example because it's already factored for us. And if we know our tricks about multiplicities, there's very little to do with this problem. First of all, since it's already factored, we know its roots. We know this thing is going to have roots at 0, at 6, and at minus 5. So let's put a number line down that has a minus 5, a 0, and a 6 on it. And now let's pick a single test point. This time, 0 won't work as a test point because it's an end point. It's a critical point. It's a 0, actually, of this polynomial. And so we need to pick a different test point. I think 1 is probably a pretty good test point. And if I plug 1 into this function, keep in mind that we don't have to worry about what the exact value is. We can calculate that, but really what we're concerned about is where is it less than 0? In other words, where is it negative? And so 1 here would be a negative, but squaring it makes it positive. And here would be another positive. So we have positive, positive, positive. This is all going to be positive in the end. Now we could get the rest of them by using multiplicity. Our polynomial has at 6 a root with even multiplicity, 2, 4, 6, etc. And so because it has even multiplicity, it's actually going to keep its sign as we go from one side to the other. That's because changing this from either just below 6 or just above 6 is still going to be a positive value and so not change the sign of the overall product. On the other hand, at 0, 0 has odd multiplicity. Changing the sign from just below to just above 0 will change the sign overall. And so we could also plug in a test value, plug in minus 1 and see what you get. But through either deduction, either knowing that there'll be a sign change because of odd multiplicity, or plugging in a test point and seeing what you get as far as sign is concerned, we know this is going to be negative. And likewise, at negative 5, we have odd multiplicity here as well. Odd multiplicity indicates a sign change, and so we wind up with a positive here. The question asks, where is it less than 0? And that's only going to happen in one place on our graph between minus 5 and 0 itself. Let's repeat that process for problem 6. I have roots at 6, minus 8, and positive 4. And so putting these down on a graph in order, we have the following. It need not be to scale. We're just interested in the sign, and specifically, where is this function going to be greater than 0? We don't have 0 as a critical value, so we could plug it in as a test point here. And if I plug this in, I get a negative, a positive, and a negative, but squared, which makes it positive. So since this is negative, positive, positive, we're going to wind up with an overall negative term between negative 8 and 4. Now we can go through and use our multiplicities. At negative 8, it's got odd multiplicity, so it changes sign. At positive 4, it has even multiplicity, so it keeps its sign. And then again at 6, it has odd multiplicity, so it changes its sign back to positive. The question is, where is this positive? So we can write that as being between negative infinity and minus 8, together with between 6 and positive infinity. Here we have something pretty similar, it's just it hasn't been factored yet. So let's factor it and see if we can get an answer. Now, if we wind up with a complex value, there is no real number then for which this would be satisfied. And we're really only concerned about the real numbers when we discuss inequalities. I can go into that more perhaps in a later video series, but the complex numbers don't accept a notion of less than and greater than that is everywhere defined unambiguously. and shares all the properties that inequalities do with the real numbers. So because the complex numbers in inequalities don't necessarily play nice all the time, whenever we talk about inequalities in this class, we're going to be talking about real values only. So if we wind up with complex answers to the polynomial, we're going to write no solution. Let's begin. First, I would set everything equal to 0 by moving it to the other side. Then I would factor, if possible. We have p and p. We have a plus, and factors of 24 with a sum of 11 are 8 and 3. This gives me the following two critical values on my number line, and I can plug in test values to see where I should shade. If I plug in 0, I wind up with a positive times a positive. That's going to be positive here. And these each have multiplicity 1, so we're going to change sign across every single critical value. The question is, where is it less than or equal to 0, meaning where is it negative? It'll be equal to 0 at these endpoints, and it'll be less than 0 between them. So we would say that the solution would be between -8 and -3 inclusively. And that's that. Here we're given another graph, and they ask us, where is this graph greater than 0? Where is the function value or the y value greater than or equal to 0? And what we want to do is think about what this means visually. These, again, are going to be regions where we are in the upper half plane. And so just to mark that on my function, that's all this region here up to this point where we're equal to 0. And then all this region here. And it looks like we have an asymptote going on here. So this is going to keep going, getting closer and closer, but never actually getting to 0. So where am I 0 on this graph? I'm 0 here. And notice that we have a possibility of changing sign here from negative to positive around this vertical asymptote. Here from negative to positive around this vertical asymptote. So we see that these rational functions could have sign changes either at their zeros or at their vertical asymptotes. Well, let's put a pin in that. Let's go back and first say, where is this positive? It looks like this is down at -3, and we do not include -3 because it is actually undefined at -3. It's sort of strung out between positive and negative infinity. Then it goes up to and includes -1. It includes -1 because we're talking about inclusive inequality here. It's just not equal to 0 at -3. It's undefined at -3, so we still don't include it. Likewise, we would take this union together with 0 itself. It looks like it has a vertical asymptote at the origin, and then goes on to infinity without ever quite getting to 0. And we don't include infinities ever. We put that in parentheses. So there is my answer in interval notation for where is this graph positive or 0. Here we have another question. Again, now a more algebraic question versus a geometrical question based on a graph. We want to know, where is this thing greater than or equal to 0? Again, so that's only going to happen at the zeros of a function or at the places where it's undefined, which will be the zeros of the denominator. So what we want to do is we want to map those out. This has a 0 at 4. This has a 0 at -7, and this has a 0 at +6. These are my critical values. Let's put those on a number line. -7, 4, and 6. And we want to keep track of which ones come from a denominator, because those we're never going to include. So let's be sure to maybe circle those, or at least think about them specially, right, when we're doing this process. But we're still able to plug in test points. We could still go back here and say, what about at 0, where this is 0, this is 0, and this is 0? Then we would have a negative divided by a positive times a negative, which is negative over negative, which is positive. So we find that at 0, which is between these two, we have a positive value. Our trick about multiplicities works even for rational functions. Each one of these terms has multiplicity 1, and so we automatically know that it's going to change sign across each critical point, giving me the following arrangement of positives and negatives. You could also plug in test points from each region, but it's quite a bit faster to make this note about even and odd numbers in the multiplicity and use that to fill out your sign changes. Now the question is, where is it greater than or equal to 0? So let's fill that out. That would be between -7 and 4. We would include the 4, but we would not include the -7. That's because the function's not equal to 0 there, it's undefined. Likewise, we would not include 6. That also came from a denominator 0, and we'd go up to infinity and not include that because it's infinity. And that would be the interval notation for this problem. Here we have another. We need to first factor this denominator. This says x minus 2 over x plus 4 times x minus 4. When is that less than 0? So what we do is we make our number line. We plot our critical values at minus 4, 2, and positive 4. We note that 0 is in fact a good test value. I would prefer to use 0 when possible. And plugging in 0, we get minus 2, positive 4, and negative 4. That gives me a negative times a positive over a negative. That's overall positive. So we know this region will be positive. Each of these has multiplicity 1, so it changes sign at every value. At minus 4 and positive 4, our 0 would be in the denominator and the overall expression would be undefined, so we want to leave those out. And the question is, where is it negative, which will be in these two regions. So we write from negative infinity up to minus 4, excluding it, together with positive 2 up to positive 4, and we exclude both these because this is a strict inequality, right? We're not going to want to include any endpoint when we deal with strict inequality. We have one more to do. Notice here, we don't actually have it set equal to 0 yet. All of our previous problems had 0 in this position on the other side of the inequality. That's really what we want to get to. So let's first manipulate the equation until that happens. We have x plus 5 over x plus 8, and this is greater than minus 1. We want to be careful in multiplying by x plus 8 because we don't actually know if that is positive or negative. It really depends on what x is. And so instead, let's try to make our move so that we don't have to bring into question how does the inequality flip. We could do that by adding 1 to both sides. Then we would have x plus 5 over x plus 8 plus 1. That would be greater than 0. How do I add those two together? Well, I'm going to need to get plus 1 in terms of x plus 8s. We need to get like bases. So x plus 5 over x plus 8 plus x plus 8 over x plus 8 would give me, combining like terms and putting this over a common x plus 8, 2x plus 13. Now this has zeros where 2x plus 13 is equal to 0. That's of course at x equals negative 13 over 2, or negative 6.5. Here we have negative 8, so let's mark a number line with minus 8 and minus 13 over 2. If I were to plug in 0, we could see that this would be overall positive, because we'd have 13 over 8. And if I were to then change sign around these critical values, each with multiplicity 1, then we would have the following changes of sign: a minus here and a plus here. The question is, where is it greater than 0? And so we're definitely going to exclude this one because it's a division by 0, but we're also going to exclude this one because it's not going to be strict inequality. So we would go from minus infinity up to minus 8, together with minus 13 over 2 up to infinity. Now, I should point out that if you have a graphing calculator, one way to approach checking your work is to graph these things. So here I've opened up a Desmos graph. My problem is x plus 5 over x plus 8 is greater than minus 1. Here's a graph of x plus 5 over x plus 8. We can see it looks like a hyperbola, the usual 1 over x shape, with slightly different asymptote and signed behavior. Now the question was related to minus 1. So let's actually plot the line minus 1. And the question was, where will it be greater than this? And noting that we have a vertical asymptote at minus 8, we can start to get a picture about where is it actually greater than the blue line, right? Where is this curve greater than this curve? Where does it have a larger y value? Well, it has a larger y value here. Then after the asymptote, it doesn't. It has a smaller one until it gets to this point, which is negative 6.5 or negative 13 over 2. And then thereafter, it does have a higher value. So this tells us that our algebra is absolutely correct, and it gives us a graphical interpretation in terms of the y values about what our inequality means. Alrighty, thank you for your patience. Have a great day. That concludes this video. Good luck with your studies, and I'll see you in the next one.